Good. So let's talk about energy balances then. That is the first topic of proper talking for this class. Okay. Okay, this is a view of the handout I prepared and is already uploaded. Typically, I write a lot on the whiteboard, but my experience from and students make notes on their notebooks. My experience from last semester is that few people take notes in online classes. So what I decided to do is I'm going to go over these notes. So all of you see the notes. I still recommend you take notes, at least occasionally. And in some cases, what I will try to do is to put on the whiteboard and write some things in there, so you see how I would go about solving the problem manually. But overall, I think, at least for this unit, the content is quite well explained in the handout. And what I'm going to do is go over it and emphasize the key points, so when you study it, you're familiar with it. So about energy balances, we're going to discuss the concept of a control volume. We're going to discuss the concept of energy balance. And then we're going to start talking about some particular aspects of the energy balance, in concrete, about the heat stored. And we'll get to see part of this today. And then for the rest of the week, we're going to discuss a balance of energy rates, not just a batch balance. And one of the things we're going to discuss that I care especially is the concept of advection, that is not well treated in pretty much any heat transfer book I found, but it's very important to discuss on open systems. Okay, the class starts right now. We are going to introduce our first concept, and it's the concept of control volume. Let's see. The concept of control volume. So what is a control volume? A control volume is something very simple. That is, as an imaginary surface that divides inside, it divides inside from outside, and that's it. You would imagine the definition would be a lot more complex, but no, this simple thing is the first step of a very, very high stairs. So each step seems small, but if we keep going up and up and up and up, we're going to reach very high. So it's important to build a solid foundation. What are the properties of a control volume? It is a closed surface, right? It's even open systems have a closed control volume. So control volume is always closed. And through this surface that you see here, let's see if through this surface you see here, you have a flow of mass that can come in or out, and a flow of heat that can come in or out. And this is all we do, because by defining this control volume, it's a little bit like a bank account into which things come in and some things come out. And we can ask, how much mass do we have? How much energy do we have? When there are no mass flows, when there are no mass flows through the surface, no mass flows, this is a closed system. When there is no heat flow is what we call an adiabatic system. Right? And you already heard these words before, but this is the definition. The control volume can move or deform in time. it's for example, can move with the flow, and this is what is called Lagrangian coordinates, or might be a static control volume through which the mass flows, and this is what is called Eulerian. Okay, about the control volume, there's a convention. So although in this class, only in the assignments, I'm going to be asking you to write a control volume. Typically, when you do a heat transfer problem, you'll be making drawings of control volume very often. So control volumes, we're going to do them as we're going to do control volumes as a dashed line. And there's something important. The dashed line is typically on one side of the line or the other side of a line, but never over a line. And sometimes it doesn't matter all that much. Some other times it's crucial. For example, if you have melting right at the interface, you have a flow of energy related to the latent heat. We'll see what that is later. So if you put the line once the control volume on one side of the surface, you might be including the latent heat, and if you put it on the other side of the surface, you might not be including the latent heat. So that's the convention for making control volumes. You mark them with a dashed line, just inside or just outside the surface you care about. Great. Control volume, just a dashed line, period. Now, second important concept in this class, and everything builds on this concept, is the concept of energy balance. It's deceivingly simple, because the energy balance sounds like a trivial thing, but is extremely powerful. And it's this one that we have here. And it reads like this. First of all, the capital Q means amount of energy. So it's joules. This is a batch energy balance. So if we have a control volume, an important thing is not if you have a control volume. You cannot write an energy balance without having a control volume assigned to it. So this equation you see here, equation 1, the first equation we see in this class, we'll see many. This equation only makes sense when you have a control volume assigned to it. This big Q is amount of heat associated with this control volume in joules. And we have 4 terms here. We have Qn, that means the heat that came into the control volume, thermal energy that came into a control volume. Then we have Q out, that is heat that went across across the surface of the control volume from inside to the outside. So if you cross the let's make a control volume here. So if I cross with energy the boundary, that is Q in. Whatever leaves the control volume, Q out. And then we have 2 more terms. One is heat generated. Qgen is heat generated inside the control volume. For example, we might have a radioactive pellet. For example, we might have we can have like a radioactive pellet that would be generating heat inside the control volume. We can have resistive heating. There are so many ways. For those of you into gaming, you might use a Peltier cooling system, right? A Peltier cooling system, you make current flow and the current absorbs heat volumetrically, right? So these things in which energy is gained or thermal energy is gained or lost inside the control volume, right? That's the QGen term. And the last term is Q stored. So much like a bank account, as I mentioned before, we can have thermal energy coming in, can have thermal energy going out. We can have, that is much like you get your salary in, you pay your rent, goes out, and then the money you had in the bank can generate some amount of interest. These days it's pretty small, but that amount of interest generated, right, is like the heat generated. And then the last part of this equation is the Q stored. And the Q stored, what is it? Is, well, how much thermal energy is stored would be your account balance, right? Salary in, rent out, interest is accumulated, it starts to be generated, and all together is how much is your bank account, your is your account balance, right? And that's the heat stored. This equation that seems so simple is crucial. So if in this class or ever about heat transfer, you find stumped and you don't know what to do, you start by writing this equation. So there are two types of problems here in heat transfer. Those in which you know what to do, and I'm not going to worry about that because you know what to do. And those in which you don't know what to do, and then you write this equation. That's it. So let's talk a little bit more about the heat stored. Let's talk a little bit more about the heat stored. You guys already had thermodynamics, and this is exactly what this is, but we're going to put it in context. We're going to put it to a good use, and we're going to build on it in our design of engineering equipment, such as heat exchangers or CPUs. So how do we calculate this heat stored? It's actually looks very easy, as is the heat stored between two moments in time 1 and time 2, and would be mass times you see this I here. This I is enthalpy. It's not the imaginary number. You might be used to see enthalpy as the letter H, and I have seen that most of the time as letter H. I will use a letter I, which is common in mechanical engineering. And the reason is that H we use for heat transfer coefficient. And half of this class will just be about the calculation of H. And I don't want you to be confused between enthalpy and heat transfer coefficient. So I'm using this notation that I didn't invent, but it's less common, in which enthalpy is I. So what this says is, this enthalpy here we have in joules per kilogram. Enthalpy is the measure of thermal energy of something. It's thermal energy. And it doesn't have a well-defined zero, right? It's a relative measure. So when I write I2 or I1 means joule per kilograms with reference to some arbitrary zero. I'm not saying what the arbitrary zero right now is. And what you're going to see is that in every equation we write in this class, this arbitrary zero would cancel out. So we don't need to worry about what the reference point for the enthalpy is. So because the enthalpy is joule per kilogram, so at time 2, I need to do mass times enthalpy, right? Because joules per kilogram, and that will be joules. And instant 1 is mass at time 1, enthalpy at time 1. Again, these equations look oh so trivial, but they have to become part of our language. One of the difficult things of this class of heat transfer is that it's like learning a language. It might not be so difficult, but we have to do it without thinking. And I know about this because my native language is not English, it's Spanish, but I have to take exams and take my candidacy exam. And now I'm teaching in English and I don't have time to stop and translate. Has to become second nature. And these little things like what is Q stored and what is enthalpy, that has to become second nature, not just for this class, because you'll be using this for the rest of your courses you take, right? In courses like design. Okay, as we talk about heat stored, right now we see something interesting. Of course, if I increase my enthalpy, I would increase my heat stored. That's the easy part. But there's another heat transfer mechanism that does not, that heat transfer books don't mention properly, although they use it without saying it, and has been confusing for students, but will not be confusing to you because I'm being very clear and upfront about this concept. And I think you'll appreciate very much having a command of it. If I have an open system, right? An open system is still like a closed control volume, but we have mass coming in to the open system and mass going out of the open system, or maybe only comes in, or maybe only goes out, but there's flow of mass through the control volume. That flow of mass brings heat with it, brings thermal energy, and that is what is called advection. So let's make this concept of advection concrete. So here we have Q stored, this formula, this equation number 3, you already seen, is mass times enthalpy at times 2 and minus mass times enthalpy at time 1. Let's say we added delta M. So at time 1, we have mass M. At time 2, we have mass M plus delta M, right? And the heat stored in this case would be, okay, I forgot to mention something important. And let's say that mass M was at a given temperature, and let's say that the mass delta M that I'm adding up is at the same temperature. For example, I can have a half full glass of water at 20 degrees C, and I add water to make it a full glass of water at 20 degrees C. It was always at 20 degrees C. Did it get hotter? It did not get hotter. The temperature is the same, 20 degrees C. Did it gain thermal energy? Yes, it gained thermal energy because now it has twice the amount of mass. So this amount of thermal energy that was gained just because we added mass, this is what is called advection. And it's a very, very important concept, which we will be using later on. To give you an idea, heat exchangers work on advection. The book is not all that clear about that. They put some formulas without explaining where they come from. And they come from here. In the heat exchanger, some mass comes in, can be cold or can be hot, and some mass leaves the opposite way, either hotter or colder. So if we have a control volume and we assume that there are no heat losses, just for now, so the Q out is 0 and there's no Q generation, the amount of heat that went in, which is this delta M times enthalpy, this is the Q of advection. Very, 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 and if we took it out, that would be heat that was lost by advection. And although this amount of heat would be dependent on the arbitrary reference we pick for advection, we're going to see that in every equation we write in the class, they end up canceling out. Actually, I don't even know any case in which they don't cancel out. Good about advection, very important concept. So now, another important concept that you know from your thermal class, and it's the concept of specific heat, is what people tend to call CP, right? You have specific heat at constant pressure and specific heat at constant volume, CP and CV. In this class, we are going to deal with heat transfer in which the mechanical action of compression or expansion does not affect the thermal balance, right? So to some extent, some people would say incompressible fluids, right? Although air, and in some occasions, we're going to see effects of compressibility. But the difference between CP and CV in a gas is the effect of this mechanical work on the thermal balance. In this class, we will not worry about this. And in our class, CP and CV are going to be much the same, right? And so here we have, I write it only as C. And typically when we deal with gases, will be in conditions of constant pressure. So it would be the CP. And how do we define this specific heat? Specific heat is the derivative of enthalpy with temperature. So in here we have a schematic, and this will be the last we discuss in the class today, in which in the horizontal axis we have temperature. And we're talking about temperature of something that could be, for example, water. On the vertical axis, we have enthalpy. So with more temperature, the enthalpy of the water increases. In this case would be ice. If it is very cold, okay, let's do it here. The temperature of the water increases with more temperature. Now, if the temperature reaches boiling point, then it evaporates. And if the temperature is too cold, then it solidifies and becomes ice. So at this point, all I'm saying is that specific heat is the slope of the curve of enthalpy versus temperature. So each 150, we're going to stop here. And if any of you has comments or thoughts of how we can do better in the class, I'm very eager to hear. Remote teaching is new to all of us, and I really care that to do the best I can for you. And I think my own learning is going to be great. If you take a look at the schedule assignments and quizzes, and you find a conflict of interest, please let me know. A conflict of schedule, please let me know immediately. Thank you very much, and let's stop the class here. I'll see you on Wednesday.